All right, so quickly, I want to get a few more things out before we stop. Boltzmann distribution, okay? Reminder, it tells us the probability of finding a molecule in a given energy level at a given temp, okay? And if you have a new temp, you need to do a new calculation. You need to know the available energy levels. And you may or may not need N total, okay? Keeping in mind that we always expect this. So the general form, sort of a general formula for describing Boltzmann's distribution, remember it's a probability. Sort of general formula, general function for this is P sub j is equal to a capital A e raised to negative beta times u sub j, where P sub j is equal to the probability of finding a molecule in the jth level, jth energy level, and U sub j is equal to the energy of that jth energy level. And capital A and this beta are constants. Now the reason I give you this form is because this general form of equation is super useful in a whole lot of other courses, other applications. You might see something that looks a lot like it elsewhere, right? It's just an exponentially decaying function. But what we're going to do in this class is we have a particular set of values for our constants that we're interested in, okay? So to define A and B for this class, right, we'll define, for our purposes. We have a couple other things we know. So we know that P sub j has to be equal to 1. T is the total number of energy levels we have, okay, starting from our ground state up to however many we have. The sum of all those probabilities better be 1. P sub j is also equal to the number of molecules in the jth level over the total, if we have that piece of information. We know that the sum of all the numbers, it's super whispery, it's driving me nuts. Okay. Give me my final 5 minutes, please. Okay. So the number of molecules has to equal the total if I sum over all of the levels. This is conservation of mass. Constant total number of molecules. And then I also know I have conservation of energy. So the number of molecules in a given level times the energy of that level, if I sum that up over all the energy levels I have, this will be equal to U total, constant total energy, conservation of energy, or first law. So then we define our constant A. What we're going to do is we're going to take this equation here. Actually, let's take this equation up here and apply the summation to each side of the general form. Okay. Also keeping in mind that this has to be equal to, once we apply the summation, equal to 1. The sum over all of the levels is going to be equal, the sum of the probabilities over all the levels has to be equal to 1, and this would be equal to the sum over all the levels. This is just being plugged in for this term here. So this is just being plugged in to this value right here. A is equal to e to the negative beta times u sub j. So I can rearrange this, I can pull a out in front. This would be equal to 1, okay? Then I can move this over to the bottom to get a by itself. A is equal to 1 over, this is the sum. So again, this is a generic form of the equation. This is a general formula for this type of equation. Okay. Our beta here that we're interested in for Boltzmann is equal to 1 over kBt, right? If we plug that in, we now have the sum over all of our Boltzmann factors for the different levels on the bottom, okay? This term is Boltzmann factor if we let beta be equal to 1 over kBt. Okay? The derivation of this beta term is on pages 364 and 65. And then we are going to call this term here Q, okay, or partition function. Q is called partition function. It is equal to the sum over all the energy levels we have. It is a sum of our Boltzmann factors for each energy level. Sum over all the levels that we have. One of the things I want to point out, this is Q. This is called partition function. Like I said, it's given by capital Q. This is the equation for it. This is called canonical form, or reduced form, general form, a whole bunch of things. Okay. The form that we are going to use in this class, it's also the only form given in your book. What we will use, and this is new this year, so I really want you to pay attention to this. A lowercase g sub j, okay? This is a weighting factor. And what it does is basically if there are different ways to be in one energy level, okay? There's ground state, probably ground state, but maybe there are 2 ways to be in ground state that are equivalent, okay? This builds in redundancy or degeneracy. If there's a level that can be achieved in more than one way, we need to consider that 2 times or 4 times or however many ways there are. Okay, and so we'll look at examples. The reason I draw your attention to this is in past semesters I've used a capital N sub j, which looks a lot like total number of molecules. Okay, so we're moving to G, which is what you'll find on the internet. Okay, and then the last thing I want to say before we go, we'll do examples where we actually calculate a partition function next time. But what partition function can tell us? Okay. Partition function tells us how particles partition. What's up, guys? Oh, you're here, great. Give me 1 second. These are how they are like spread or divided over the accessible energy levels. Can you see this? Levels. At a given temp. Right? This is important, given temp. Another sort of way to think of this is thermal accessibility. So at a given temperature, how can things distribute? And just, I want to reiterate, as temp goes up, U sub j over Boltzmann times temp goes down, but negative U sub j over Boltzmann times temp goes up. Okay. And we'll leave it at that for today.